Welcome to Study Loop.
So if we look at the diagram over here, we see that we have a star and then we have a planet. So let's mark this. So that's the planet of that star, and the distance between the star and the planet is r, which is same as the Sun-Earth system. So if we look at the geometry, we can see that we can draw a line around here, and then this line becomes parallel to this line, so this angle becomes theta, and r is basically the distance between earth and sun, and the distance from earth sun to star is d, because the distance from star to earth is d, and we can say the same thing for star to sun, because it's a this distance is this distance is larger than r, so we can approximate these two lines to be same. So in that sense, this theta should be equal to uh, theta times d should be equal to r, or in other words, theta should be equal to r over d. Right, so and theta is the angular resolution. So if we are in Earth and if we want to see the star and this planet separately, we need this angular resolution. So we can actually get rid of this part now. Yeah, we don't need this part. And if we do so, the picture will be clearer. So there we go. So yeah, we don't need the radius as well. So this is the part that we're interested in now. So if we look at this part, we see that we have this earth, and from earth we can, if we want to differentiate the star and the planet, we need an angular resolution of theta, and the distance from earth to the planet or the star is d, because this d is very greater than r, so we can write theta as r over d. And from equation 25.7, we find the expression for angular resolution, which is 1.22 times lambda, which is the wavelength, times the divided by the diameter of the telescope. So that's the unknown that we need to solve. So if we write d in terms of the other terms like r and d, we get something like 1.22 times lambda times d divided by r. So we know all the values. Let's write it here. D is going to be 1.22 lambda times d divided by r, where lambda is 550 nanometers. So that if we convert that to meters, it's going to be 10 to the power minus 9. Then we have 4 light years. So 4 light years, that's the d here, the distance from earth to uh, sun, or earth to the planet, whatever we want to call it. So that's going to be, and if we convert that to meters, that's going to be 9.461 times 10 to the power 15 meters over light year. So that's 1 light years times 4 light years. So we converted this light years to meters, and then for r, it's 1 AU, 1 astronomical unit, and that's going to be 1 AU, and if we convert that to meters, this will be 1.496 times 10 to the power 11 meters by AU. So we get rid of AU and we have meters here. Right, so if we plug in all the numbers, we get D as 0.17 meters, or roughly 17 centimeters. So that's the minimum diameter that we need to resolve the planet and the star. Thank you.